Hey everyone, and welcome back to the Foundry by Forge College. Today, we're stepping into the shoes of a data detective. Now, unlike the detectives you see on TV, we don't get dramatic confessions in dimly lit rooms. Nope, we just get thousands and thousands of lines of CSV files. You see, when you're building on Solana and really digging into these advanced Solana concepts, you generate a massive amount of raw simulation data. But here's the thing. Raw data is just a crime scene. It's chaotic, it's messy, and honestly, it doesn't actually tell you who the culprit is. So in today's explainer, we're going to take that chaotic evidence from our previous lesson on simulating sharded data transfer, and we're going to find the absolute perfect Solana data sharding strategy. We'll evaluate performance, optimize network speed, and ultimately figure out exactly how to scale effectively.
So here is the blueprint for our investigation today. We'll quickly look at the core sharding trade-off, introduce our key metrics, run them all through a comparison pipeline, translate those traces into real deployment guidance, and then deliver our final verdict. Simple enough, right? Let's get to work. All right, part one, the sharding trade-off, or as I like to call it, the moving boxes dilemma. Okay, let's dive into this. In our previous lesson, we generated a literal mountain of data traces, but no actual answers. To really understand the core conflict here, let's use an analogy. Imagine you're moving out of your apartment. On one hand, you have the finer shards approach. This is like packing your entire life into hundreds of tiny shoebox-sized boxes. Now, you can hand these tiny boxes to a dozen friends, and they can load up the moving truck incredibly fast, all working at the same time. That's your fast parallel transfer. But what happens when you finally get to the new place? You have to open hundreds of tiny boxes just to find your coffee maker. The reassembly cost is a total nightmare. Now, on the flip side, we have larger shards. This is like renting 3 massive wooden crates and just tossing all your furniture inside. Loading the truck is way slower. It takes 4 people just to lift 1 crate. But unpacking, you literally just pop the lid and boom, your entire living room is right there. Super low reassembly cost. So that is our fundamental trade-off: raw transmission speed versus coordination cost. Moving right along to section 2, meet the key metrics, aka the suspects. To figure out whether we should be using the shoe boxes or the giant crates for our Solana deployment, we really need to interrogate our suspects, our core metrics. And let's start with the most notorious one, average latency. Honestly, average latency is a liar. It completely hides the painful truth of what your users are actually experiencing. I mean, imagine 10 people at a restaurant. 9 of them get their food in 5 minutes, but the 10th person waits an hour. The average wait time looks pretty fantastic, but I guarantee you that 10th person is never coming back. That's exactly why we look at P95 latency instead. It tells us the latency at the 95th percentile. It isolates that tricky tail end of the data, showing us the worst-case scenario that a significant chunk of our users will actually feel. If you want your app to feel truly responsive, you absolutely have to tame the P95 tail. So here is the full lineup in our interrogation room. We have P95 latency, which we just talked about. It implies how snappy the network actually feels to the end user. Then we have throughput, measured in bytes per second. This is your network's raw muscle. It dictates the capacity and bandwidth requirements per node. Next up is coordination time. This is the sum of all those pesky per event overheads. Going back to our moving analogy, this is the time spent taping up boxes and writing labels. On a Solana node, it represents synchronization costs and CPU overhead. And finally, the retransmission rate. This is the ratio of events that failed and had to be sent all over again. A high rate here means you're just throwing precious bandwidth out the window, pointing to a potentially unreliable network setup. So what does this all mean? We know the trade-offs and we know our metrics, but we still have thousands and thousands of lines of CSV data from our simulations, just a massive, intimidating wall of numbers. How do we actually translate that raw, chaotic data into a clear, objective winner? Which brings us to section 3, the comparison pipeline, essentially our interrogation room. And this brilliantly illustrates how we actually process all of this. We use a lightweight Python metric aggregator script. Basically, the code takes those raw CSV traces, reads the timestamps, and groups the events by their specific shard ID. It calculates the latencies for successful events, sums up the transferred bytes to figure out our total throughput, and checks for any of those dreaded retransmission flags we talked about. It takes the scattered, chaotic behavior of thousands of individual chunks and rolls them up into nice, neat global aggregates. It does all the heavy mathematical lifting so we can step back and actually look at the macro picture. All right, section 4, traces to deployment guidance, or cracking the case. Standardizing this whole evaluation process is actually a core practice we teach in the advanced courses at Forge College.
Let's move to and see how this builds into a reliable, repeatable workflow for cracking the case. Step 1, standardize your inputs. Make sure your Unix are consistent, seconds for time, bytes for size, no mixed signals. Step 2, compute those base metrics using the pipeline we just looked at. Step 3, normalize and score. Step 4 is statistical validation, which is absolutely crucial, and we'll unpack that in a second. And step 5, translate to system impact. This is where you turn those raw numbers into actual, tangible load expectations for your validators. Let's actually zoom in on step 3 for a second. Normalization. Think about it. If strategy A gives you a P95 latency of 10 milliseconds and strategy B gives you 500 milliseconds, you can't just add those raw numbers to your throughput bytes. It's totally apples to oranges. So we normalize everything onto a clean, standardized 0 to 100 scale. 10 milliseconds might score a perfect 100, while 500 milliseconds scores a 0. You do this for all your metrics, apply weights based on what your specific project needs most, and suddenly, magically, you have a definitive composite score. Actually, wait, scratch that. Don't go deploying to mainnet just yet. Step 4 was statistical validation, specifically using bootstrap confidence intervals. Look, a single simulation run is about as reliable as a single eyewitness at a chaotic scene. There is variance. You might have just gotten a lucky simulation run. To be absolutely sure, we run repeated samples of the data. If the 95% confidence intervals of your composite scores overlap, it means the winner isn't actually clear. Your decision is fragile. Never, ever make a major network routing decision without ensuring your statistical intervals do not overlap. And finally, section 5, the verdict on sharding. Time to close the case. So, the crucial point is this. We've done the math, we've checked the intervals, and we've survived the interrogation room. How do we turn all of this into concrete deployment guidance? Well, it boils down to 3 rapid-fire synthesis principles. First, metric selection shapes the winner. If you weigh throughput heavily, one strategy is going to win. If you weigh tail latency heavily, a completely different strategy takes the crown. Second, granularity is a lever. Finer shards give you parallel speed but cost you coordination CPU. It's just a dial you turn based on your network-specific constraints. Third, statistical robustness matters. Like we just said, never trust a single run without verifying the variance. Now, if you're going to remember just one takeaway from today's explainer, make it this actionable rule of thumb. If your environment is bandwidth scarce, meaning your network pipes are super tight, prioritize finer shards. The parallel transmission really helps squeeze that data through. But if you're building an application where low latency is absolutely critical to the user experience, prioritize larger shards. You'll significantly lower the reassembly overhead, skip the metadata synchronization delays, and keep the application feeling incredibly fast. Which brings us to our final, somewhat provocative thought for the day. Treat sharding design decisions as resource shift problems. You know, you aren't magically creating a perfect network. You're really just moving the cost around. You're shifting the burden between network bandwidth, CPU coordination, and end-user latency. Your job as a Web3 builder is to figure out how to put that burden exactly where your specific system can handle it best. And with that, our case is officially closed for today. Make sure you take these standardized metric outputs and bring them with you to our next lesson where we'll tackle protocol interactions. And as always, to master these concepts and dive deeper into Web3 engineering, visit forge.college. Thanks so much for joining me on this explainer, and I'll see you next time.